Okay, so now let's return to the example of diffraction from a half plane. So at this point, you may want to return to the GTD lecture and just refresh your memory about how that worked out, because I'm not going to repeat all the details here. What happens in this problem is we're interested in a half plane. We end up with a cylindrical wave with this very simple phase factor. Really, all the work is in computing the diffraction coefficient. Rho super c is infinite, beta naught is pi over 2. Here's how the wedge geometry works out in this case. So this is new. Now we note that in this case we say that WA, the wedge angle, is 0, so n equals 2. Before I just told you n should be 2. Now you see why n equals 2 in this more general context. And of course this is the 0 face because the source is over here. And this is the n face. So previously I showed you what the diffraction coefficients looked like for GTD. So here is the distance normalized soft diffraction coefficient in linear units. Here is the angle to the field point, phi super d. As you recall, GTD did this thing where it started off low and then exploded here at the shadow boundary. So there's a shadow boundary in the geo field here, shadow boundary in the geo field here. But otherwise, it was relatively okay. The UTD diffraction coefficient values are shown here. And you can see that they do the expected thing. That is, they are finite, for one. Not only are they finite, but they peak at 0.5. And that's a special number. It turns out that those diffraction coefficients are always 1/2 at the shadow boundary. So that's a great way to check your math and do troubleshooting. Now when we construct the whole solution, this looks just like the GTD solution. Again, the only difference between the two is diffraction coefficients. So this is same as GTD in this case. So I don't need to remind you about any of these details. And again, this is the same as the GTD solution. We have these three regions. In one region, we have all three fields, incident, reflected, and diffracted. In another region, we have only incident and diffracted. In the third region, we have just diffracted. And here is the expression for the diffracted field. And there's the diffraction coefficient. So the entire difference between GTD and UTD is in that factor d sub s. Here are the fields. So this is incident. This is the magnitude of the incident field as a function of phi, the angle to the field point, measured from the 0 face. The incident field is a constant until we get to the incident shadow boundary. Here is the reflected field. It's a constant until we get to the reflection shadow boundary. And remember, these phases depend on the path lengths. So these two things are interfering with each other. And then finally we have UTD diffracted. And what happens here is we see the UTD diffraction is very small. It peaks up, it comes back down, it peaks up, it comes back down. And we see that's exactly 1/2 the value of the field at the discontinuity. So this, again, is a very useful thing to know about UTD and diffraction in general, that the diffracted field must be half the value of the field at the point which is discontinuous at the geo shadow boundaries. So here I'm plotting the geo solution. Again, I've already shown you this in a previous lecture. This is incident plus reflected as a function of direction to the field point or angle to the field point. What we see here is this is all reflected. And this is incident plus reflected. So the reason this oscillates is because the incident reflected fields are going in and out of phase with each other. So when they're in phase, we get a value of 2. When they're out of phase, we get a value of 0. Now, when we add the UTD diffracted field to this, two things should happen. One is we should get a non-zero value everywhere, but we should also see no discontinuities. We should not see discontinuity here, and we should not see discontinuity here. In fact, that's what happens. We see we go smoothly from region 1 into region 2, and we go smoothly from region 2 into region 3. This concludes this lecture on the uniform geometrical theory of diffraction.